Why exactly does this work? It's clearly seen that while one banana chunk is smaller than all the others, it is still floating, while larger ones have sunk. Additionally, at the same time, the largest banana slices are floating, while smaller ones have sunk. Well, we don't exactly know, but we do know it's got something to do with buoyancy. Before we go into buoyancy, however, let's take a quick look at density to make sure we understand some of the underlying principles of the interactions of solids and liquids. As we see here, this strawberry floats in water, while a domino dropped into water sinks. But why precisely is this? The explanation lies in density. If you were to examine the arrangement of the molecules and even the spacing of the atoms within the molecules involved in the demonstration with the strawberry and the domino, you would find that the molecules of the water are spaced farther apart than the molecules of the domino, and then the molecules in the strawberry are spaced even farther apart than those in the water. So why does this matter? Because in fact, what is happening when something floats or sinks in a fluid is that because the fluid lacks the rigid structure of solids, the molecules within them are free to move about in responses to forces acting on them. So when something is more dense than water, the force of gravity exerted upon that thing is greater in a given volume than is the force of gravity exerted upon water in that same volume. And so the thing sinks. But when an item is less dense than water, gravity exerts less of a force on the smaller amount of mass it contains in a given volume, and so it floats. But what about something that neither sinks nor floats, like this egg dropped in salt water? Most people haven't seen something like this, and this is because in order for a solid item to neither sink nor float in a fluid, it must have the same density as the fluid it is in, which is extremely unlikely. If one is not purposefully attempting to make such a thing happen, they won't see it. But that's enough about density. If something can float or remain neutral in water, then something must be exerting a force upward on the egg. But what could be doing that? The answer is buoyancy. So let's take a look at how this works. Ever noticed in a pool that the farther down you go, the more you feel a squeezing sensation? We call this pressure. It's defined by the amount of force over an area. So when you're at the bottom of a swimming pool, there's a greater pressure on your ears, just like with our egg. When the bottom is deeper in the salt water than the top, there's a greater pressure on it, and a greater upward force. This is explained by a difference in kinetic energy and potential energy surrounding the egg. As it sinks, particles of the fluid are moved out of the way, gaining potential energy with the increased height, which makes them want to move back downward, creating a greater upward force as they push on the particles with lower potential energy below them to make them want to balance out the potential energies. So now that we understand why there's a difference in pressure, let's look at how we can represent this mathematically. If we know that the force of buoyancy on a suspended object is equal to the amount of upward force minus the amount of downward force exerted by the salt water, and we know that force is equal to pressure times area, we can substitute for force, and then, since we know that pressure in a fluid is equal to its density times the acceleration due to gravity times the height of the surface in it, we can in turn substitute this for the pressure so that we have density times gravity times the height of the top and bottom of the egg. But then since we see that the difference in these heights is the height of the egg itself, we can condense this into one simple formula. The force of buoyancy on a suspended object is equal to the density of the fluid times the acceleration due to gravity times the height of the object times the area of the object. But wait! Height times area is equal to volume. So it turns out the force of buoyancy on an object is equal to the density of the medium exerting the force times the acceleration due to gravity of the object times the volume of the object? Hang on a minute there. What if the object were to float? This strawberry, for example, floats with the top above the water, but with the bottom below it. So what is volume actually referring to in our formula when it comes to something that floats? The part below the water? Or the entire volume of the object? Well, technically, it's neither. You may remember from before that when an object is placed in a liquid, that it displaces fluid particles as it moves through it or into the water. This is because liquids are largely incompressible, and so when something is placed in them, their molecules move aside to make room for the item. This is the reason the water rises whenever something is placed in it, and this brings to us one of the fundamental principles of buoyancy, the Archimedes Principle. The Archimedes Principle states that the upward force exerted on an object by buoyancy is equal to the weight of the water displaced by that object. So it turns out that the volume component of our formula for calculating the upward force of buoyancy is actually not the volume of the object, though it is the same as the volume of the submerged part of the object, but in fact it is the volume of the water, and this makes sense because the density of the water is a ratio of mass per volume. So therefore, mass can be set equal to the amount of water displaced by an object, and the volume would have to be the volume of the submerged part of the object, or in other words, the volume of the water displaced by the object. We can see that the mass of the water displaced is equal to the density of the water times the volume of the water displaced. And so, if we substitute mass in for density times volume, the equation for calculating the force of buoyancy becomes quite familiar indeed. It's the formula for the force of gravity on the displaced water, the weight of that water.